the space. Yes, so we are recording. People want to turn their video off, please do so. We'll get going in just a moment.
Hey, Jared, could you speak up a little bit, please? You're not quite as loud as you normally are.
Okay. That's right. How's that, Laura? Is that a bit better?
That's better, thank you.
Thank you. Thanks for letting me know. All right, just waiting for people to arrive. And we shall get going shortly. We have an hour and a half today. So plenty of time, plenty to get through. Looking forward to lots of discussion today. We'll have a few breaks, quite a few breaks after each of our presentations to time for Q&A. So looking forward to the input there. There we go. All right. I think we're just about ready and time to kick off. So hello and welcome to this webinar of tools and guides to accelerate heat pumps in commercial and industrial applications. Plenty of talk about heat pumps in the world. They've been around for a long time. That doesn't mean we've perfected the art of implementing them across the many different applications we expect them to be implemented in. So plenty of learnings to be shared that A2EP has gathered over the last year and a half, and to let you all know the insights and tips and tricks for how to do this. My name is Jared Leake, and I'm the CEO for the Australian Alliance for Energy Productivity. I'd like to welcome you to this webinar brought to you by our members and from the Race for 2030. As always, I'd like to kick off with an acknowledgement of country, to acknowledge the traditional custodians of country throughout Australia and their connections to land, sea and community. Pay our respects to their elders. For those of you new to A2EP, we are a member-funded industry association, and here is our wonderful broad set of members that share our passion for improving energy productivity and decarbonisation across Australia. So many thanks to our members and their ongoing support. This is the A2EP team. I'm very lucky to be joined by two of our team members today. Laura Taylor, thanks for joining, and Brendan Voss. And so they'll be joining us later for presentations and also helping on the Q&A. On the Q&A, we'll have Slido running for you today, so please enter that your questions in there. I said after each presentation today, you'll have an opportunity to ask questions, and we'll go through those, and you may have want to do a bit of a deep dive on anything that's presented. So please enter those questions there in Slido. This session is being recorded, and the slides will be sent out along with that recording sometime in the next few days, and you'll see that published on YouTube shortly. This webinar is brought to you by RACE, Reliable, Affordable, Clean Energy, the CRC that's been operating for some 4 or 5 years now and doing some fabulous work within energy productivity and all things clean energy. So yeah, the RACE focus is certainly on emission reduction and decreased energy costs for end users and targeting demand side actions within a whole of system solution. They have a fabulous innovation framing, which brings together market system design and knowledge sharing, customer preference and end user technologies and analysis. A2EP's been working with RACE right from the inception there, some coming up to 5 years ago, and done lots of projects and really enjoy the work coming out of RACE. It certainly is helping guide all the change in this energy transition that we need. So many thanks here to RACE. Just setting the scene a little bit of where we've come from. This publication that I'm flashing up here was one of the original coming from RACE, opportunity assessment, to understand the issues within process heating. And I've highlighted a couple of the actions that were identified some 4 or 5 years ago, and then we've now been able to work on those. And it's about increasing the availability and utilization of data and smart meters and doing models for process design tools. And we'll show you one of those models that's now ready towards the end today. Also increasing the confidence of renewable heat technologies and improve industry engagement. And that's certainly what we've done a lot of with these case studies and roadmaps and what have you, and building the skills to support that. Also with, again, mentioned in that other one for medium term is building industry confidence. And so you'll see put together today a whole suite of projects that come together to really tick all these boxes and help move this along. So the only way we could have done that is with some funding. And so first of all, big thank you to New South Wales Government, their business decarbonisation program. We're major supporters of this, along with the Australian Meat Processing Corporation. And that's why you'll see we've done quite some case studies around meat processing, and that has shaped the way we've developed some of these tools a bit as well. And we've done this in collaboration with UTS and RMIT. So thank you to those partners. Not here today, but we'll certainly acknowledge the work that they've done in bringing a lot of these tools to you today. Those tools, here they are. There was 6 different projects within this Race for 2030 overall project. Case studies was a great place to start to see what's happening here and now. And Laura is going to be presenting on those towards the end of the webinar today. But then we have the C&I decarbonisation roadmap. It did end up focusing much more on the commercial rather than the industrial. But we have Jordan Lim from Bridgeford's going to be presenting on that one, as they're the ones that were the main authors of that. We've got a data capture guide to help you make sure you optimise the heat pump design and getting certificates. And Northmore Gordon was the main author of that one, and we have Andrew Clark from Northmore Gordon to present on that one. When it came to refrigerants, we've now produced a guide which helps you, hopefully simplifies that selection. Brendan Voss, A2EP, is going to be presenting on that one. We did have support from ACED Consulting, but we did the A2EP was the main publisher for that one. Finally, the big one we have is the heat pump estimator tool that we're presenting today. And this is an evolution of the tool that A2EP has had over a few years, and a lot more smarts. And Brendan Voss is going to be presenting on that one. That one was developed in collaboration with UTS and RMIT, and they brought their own excellent skills to the table and has been incorporated in the tool there. There was one more project on product development report. It's a little bit specific for what government needs and to guide government policy. We're not going there today. It is available on the RACE website, and it does show you where OEMs are planning to go with their products with regards to refrigerants and what have you. So that one is available, but we're not actually going to discuss that one today. So what is the impact of this webinar and these tools? I thought the best way to show that is going to be, I think, in dollars. And let's just take a standard base case, 1 megawatt steam or hot water boiler used to generate 80 degrees of hot water, 80% efficient. If you're lucky, the overall system's probably less than that. Typical operating utilization for a boiler is about 20% of the time. And that would then say use about 9 terajoules of natural gas per year, costing somewhere around 180K of gas plus O&M on top of that. So that's the base case. And I say, if you just go out there without following a methodology, you're going to do a like-for-like replacement. You'll put in a 1 megawatt heat pump and delivering 80 degrees and what have you. And so that's likely where you'll go. That may result in an air sourced one, and probably require a dual stage heat pump to have such a high temperature lift. You'll probably only get a COP of 2.5, and you might find yourself with an extra connection requirement or transformer on site of 400 kV. That's going to cost you around $5 or $6 million. And you'll only be saving about 80K per year. Or I'll offer an alternative. If you follow a sequence of investigations and getting the right data, that's going to come down a long way. And that's what this webinar is all about. So first of all, we're saying here's a bit of a roadmap of steps to follow. Here's the data and what have you. That's the first, after knowing the roadmap and the steps, that's the first step to take, is getting that data in place. After that, it's time to just think about which refrigerant, and there's a guide there, and then maybe start a little bit of modeling to understand what the costs are going to be and how you can move things around the different drivers. And so that's what we're going to present on today. And we think that will show you how that cost could come down to from 5 or 6 million down to maybe around 1 million, with more likely 120K of savings. White certificates probably around about 15 to 20%. I've just left an X at the moment, but it's a band of 15 to 20, maybe up to 30% if you utilize the equipment more often. But typically around about 300K you may expect from that. And then all of a sudden you've got a decent payback and you can start seeing a project moving. So let's dive into our excellent lineup of speakers today. First of all, I'd like to introduce Jordan Lim from Bridgeford Group. He's going to be taking us through the roadmap. Then Andrew Clark from Northmore Gordon on the data capture, Brendan Voss on the refrigerants and the estimator tool, and then Laura's going to kick it home on the case studies. But first of all, I'd like to invite Jordan. Could I get you to start sharing your screen and kick us off with that first presentation? And by way of a quick introduction, Jordan Lim works for Bridgeford Group. I would say one of the preeminent consultants working in the commercial building space and some industrial in there, doing fabulous work on designing and sizing heat pumps for aquatic centres and commercial buildings, really leading the way, and great to have them back here for another webinar. Jordan, you're one of the main authors for this commercial roadmap. So please take us through that methodology that you've developed and this publication report that is now available. Jordan, over to you.
Hey, thanks, Jared. Looks like I don't really have to introduce myself anymore after everything that you just said. Thanks, everyone. My name's Jordan Lim. I'm the engineering group. I'm the engineering lead from Bridgeford Group. Today, I'm just here to share a bit of a guide that can hopefully help anyone who's looking to electrify their assets to prepare for electrification using heat pumps, so to speak. The aim here really is to give everyone the awareness of what can be done before you start engaging consultants to do a feasibility study or design on electrifying a building's heating system. So that afterwards you can explore more cost-efficient ways and energy-efficient ways to decarbonize your heating system later on. So we'll just quickly cover why we need to electrify, which is really one of the main things that are driven by this Race Towards 2030 initiative. Then I'll talk through why this electrification readiness assessment is important. I guess because I can't see my screen at the moment, I was wondering if I'm sharing the right screen there. Someone from the A2EP side? Great.
Yeah.
So I'll talk to why this electrification readiness assessment is important, together with briefing the two key things that can be done to help prepare an asset to be what we call quote-unquote ready for electrification, for feasibility or design. Because my topic today is more on sharing the what and the why, and my other A2EP colleagues will then take on the baton on sharing the how, probably in a different session. So just very briefly, you see here there are two graphs that represents the trajectory of gas boiler systems and heat pump systems. And so on the left there, technology speaking, we expect boilers efficiency to already plateau at around 100% efficiency, while heat pump technology is already a more energy efficient technology. It's still going to be expected to slowly improve over time in terms of its heating efficiency. Emissions wise, on the right graph here, there's still uncertainties on whether or not the gas grid will be decarbonized, but probably perhaps a different topic. But we know for sure that electricity grid is rapidly being decarbonized, and therefore one of the primary reasons for transitioning from gas heating to electric heating. So in most states in Australia at the moment, electrifying the building's heating system will typically result in emission savings already. But the graph that you're looking at here shows a likely Victoria scenario today after electrification, because in Victoria, unfortunately, we're blessed with the most polluted grid at the moment, and typically emissions of a site today in Victoria doesn't really yield much of emissions different even after electrification, but case by case, of course, but it's slowly expected to be rapidly decarbonized over time with all the renewable energy projects going on. So why are we encouraging people to take a step back and do these simple electrification readiness assessment that I'll soon go over? You may ask, rather than just go ahead and design for a heat pump space heating system. It's all got to do with costs. By doing some of these simple upfront steps, although it takes time and effort, right? But you're giving yourself the opportunity to reduce electrification costs by a fair bit down the line, potentially up to 35%. I say 35%, yeah, but like there have been case studies as explained by Jared earlier, that could achieve more than half of your cost reduction afterwards. So yeah, like I'll just, it's really just to allow everyone to electrify their portfolio without having to expend costs that are unnecessary. So first thing that asset owners can do at the facility is a heating hot water supply temperature reduction testing. What it really entails is basically assessing if a typical building heating hot water system that normally delivers 80-degree water for heating, see whether or not this can be adjusted down to a lower temperature without compromising on the building's ability to maintain the set point temperature. I'll explain in a couple of seconds, but the picture here on the right there shows a model plant with a gas-fired boiler system. So if we move on to the next slide, you can identify, if you can identify that your heating hot water plant can operate at a lower temperature, say 55 degree, for example, rather than 80 degree, you'll be able to design for a heat pump system that allows you to do what we call single stage heating, relying on just air source heat pumps only to supply you with lower temperature heating hot water, say 55 degree, for example, to deliver heating. You can see that the picture on the right there now shows a heating hot water plant with a much higher footprint requirement than the gas-fired boiler plant that was shown earlier. So this is something that asset owners need to be aware of when deciding on electrification, because while it's efficient and helps decarbonize the building, it does take up a lot of real estate. So it's not uncommon to see up to 10 to 15 times the footprint requirement of a gas boiler system for an air source heat pump heating system. Now, if you're not able to lower it down to say 50 degree or 60 degree, for example, and have to maintain up to 75 or 80 degree, what you end up needing to do when designing for a heat pump system to deliver these high temperatures is that you need a separate set of water-to-water heat pumps, or so-called water source heat pumps, which are the two smaller units just next to the larger air source units there, to basically to bring up the temperature that are supplied by these lower temp heat pumps up to the temperature that you need. But the point is that if you want higher temperature heating, this type of cascade configuration may be necessary. And while this solution's air source heat pump takes up less space compared to the previous photo, but overall your footprint requirement goes up. And now because you have more units, it's more expensive to implement too, and it's also less efficient. So what we learned here from the previous few slides, which hopefully the graphs here can provide everyone with a bit more clarity, is that heat pumps work more efficiently with lower supply temperatures. When the design temperature is lower, your footprint requirement is also smaller. And lastly, your cost will also be lower as well if your supply temperature is lower. So hopefully we all now recognize the importance of doing this heating hot water testing. And for the upcoming 2 to 3 weeks, we have other A2EP members running workshops in Melbourne and Sydney to explain how to actually do this testing and achieve the results that you want. So yeah, a lot of efforts here that's been funded and supported by A2EP and New South Wales government. You can maybe correct me if I'm wrong, Jared, after the presentation. But so hopefully everyone can benefit from these workshops if you have already signed up for them. Lastly, one simple measure that you can also apply before electrification is to submeter your heating hot water system properly, or otherwise it's already been properly submitted. You really need to get it trending enabled from your BMS, making in such a way that you can download the right data set to allow you to create a graph on the right side there that shows you a heating profile of an example building that I recently worked on. It's common knowledge that gas-fired boiler systems are oversized because they are a lot more affordable. However, for heat pumps, given that they're a lot more expensive to implement, you may not want to electrify with a similar capacity to a boiler system, but rather installing what's only necessary. But you need data to help you understand what your actual requirement is. Otherwise, there isn't really much that you can do to justify why or how your building can work just fine with a smaller heating system. Right. So hopefully this session can at least help some of you, or maybe at least the asset owners. I think we're open for question now, but my email is down below. Reach out to me if you'd like to discuss more, but thank you for listening.
Thank you so much, Jordan. On that heating hot water workshops, so we've got one next Tuesday in Melbourne, and then later in the month in Sydney. We've got some sponsorship from the likes of GeoClima on that one, who recognise that the lower you get that heating hot water temperature, the more likely you're going to go ahead with a change out. Jordan, have you been involved in much in those the practical reduction of those the heating hot water temperature, and just maybe if you got a little bit more to share on how that proceeds and how that goes?
Yeah, a lot of the temperature testing that I've actively been involved in, there are two different ways you can do it. One, which is that you really just quickly adjust the temperature from 80 degree down to aggressively down to 60 degree or 55 degree, for example. Then the moment you hear people ringing the alarm complaining about underheating, then you slowly adjust it back up to 65, and if people still complain at 65, you adjust it up to 70 again, to the point where hopefully you achieve a temperature that is lower than the existing set point, but yet doesn't necessarily compromise on the heating of the building. And of course, this is not ideal, especially for, let's say, real estate owners. But I see this testing done typically on council buildings because they have ownership of the building as well as having their own employees working in there. So it's more easily adjustable this way. But let's say if you manage the building and then you have like a tier 1 client leasing the building, for example, and then maintaining heating is really what determines whether or not they'll continue to stay with the asset. You don't want to do this because it's going to result in a lot of complaints and thereby risking the leasing opportunity in the future. So there's a guide that has already been released by A2EP that tells you some of the practical ways to go and do it without impacting the operational comfort. There are a lot of parameters that you can assess. Let's say for the temperature leaving the air handlers, for example, as well as temperature leaving the VAVs, right? You can monitor the temperature changes in those equipment rather than aggressively dropping the temperature down to 60 and waiting for complaints, right? There are things that the point is that there are things that can be done, without impacting the operational comfort, which you can read a little bit more in the guide that A2EP has released.
Thank you, Jordan. Yeah, such an important step here. I can't see any questions coming through on the Slido, but I can see something in the chat there. Let me check with Tracy Colley, you're joining us there from Race for 2030. Tracy, have you seen anything coming through? Oh, there you go. There it comes through from Penny. So we've got to, let me go straight to that question then, is examples, building heating as opposed to hot water heat needs for industry, particularly food. Probably asking too early. Oh no, never too early there, Penny. We're looking at building space heating, talking about that at the moment, getting that heating hot water temperature down for industry and for when you're talking about sterilization and what have you. That's not to say reducing those, but often it's a case of you may have steam at 120 degrees producing just 45, 50 degree hot water. And so that can be the way to look at that is don't produce the 120 first, just produce the 45, 50 first rather than going up and then come back down. If I look at looking at the chat there, a question here from Rick: can heat storage also help smooth out peak demand loads, thus reducing heat pump system size. Jordan, have you done much in the way of modelling that? We will cover
Yeah,
that off in Brendan's area in the heat pump estimator
yep.
tool with luck.
Yeah, I don't mind. I don't mind leaving for Brent afterwards, but yeah, you installing thermal storage or what we call buffer storage can definitely help smoothing out your demand. Like I think probably just very quickly numerically, 4 kiloliters, close to 4 kiloliters of buffer storage is close to about 100 kilowatt of heating supply. So if we go back to the slide earlier, if everyone can still see it, let's say this particular spike here is about 200 to 250, right? And so rather than, let's say, installing a 1.5 megawatt system, for example, if you can be certain that these spikes do not come in, let's say, in subsequent hours, let's say there's definitely going to be a gap in between before the next spike, you can size it up to, let's say, 1.25 megawatt, for example, and install 10 kiloliters of buffer storage on the site to help smoothing out the load. So your heat pump's not going, doesn't have to be the one who's supplying the heating for the additional 250, is your buffer storage just doing the work. And so that will definitely reduce the cost of implementation a little bit, but it's going to be a balancing game too, right? Because you gotta, if it, let's say for like a high-rise office, you don't necessarily have the sufficient structural loading to install your buffer storage. For example, the additional works that comes with the structure works in order to install the cheaper buffer storages can actually increase your cost too. And in the event, it's cost neutral if you compare with just installing the heat pumps, right? But I think one important thing to note is that if you install a heat pump system, you typically require to install buffer storages anyway in order to prevent the heat pump from short cycling. So what you probably want to assess is that with the minimum buffer storage requirement, how much heating capacity would they already offer, right? And then go from there.
Excellent. And I think it's just raw terms of a heat pump's $1 million per megawatt. I expect the storage to be about 10% of that or so. But we may see that fall out in when we look at the heat pump estimator tool, when Brendan's going to present on that a little bit later on. Good question here. I like this one. Is there any increase of fan power when you reduce the supply water temperature? And that's fan power on those air handling units. I've got an opinion on that one. Maybe Brendan does. Jordan, let's hear from you first on that one.
For the ones that we've done testing on, if you lower your temperature on the heating hot water side, it doesn't quite impact the fan power unless, let's say, if you have pre-existing air handler units that are meant to deliver, let's say, higher temperature, that have coils that it was meant to deliver higher temperature, once you replace it with coils with a lower temperature coil that can support lower temperature heating, obviously because the surface of area of the coils has increased as a result, and thereby increasing pressure in the air handlers, that's when you see an increase in fan power. But if you're just lowering the temperature supply at the moment, I think in terms of physics or otherwise, anecdotally from the ones that I've seen, there's not much change in fan power yet. Yeah.
So my input for that one is, you often talk about robbing Peter to pay Paul, but it would be a case of robbing Peter for 1 cent to pay Paul $1 type thing. This is the difference. So if you look at fan power, that'll be measured in watts, but the heat pump itself is measured in kilowatts or megawatts. There is a huge difference. So that, always remember that 1 degree decrease in that supply temperature will give you a 2 to 3% improvement in the COP. Brendan, what's your take on that?
Yeah, I don't want to add too much more because just timing wise, but I think a lot of what I've seen is that some of those fan systems are pretty suboptimal as already configured anyway. And often it's a really good opportunity to reconfigure it with EC fans that are probably better selected for the duty point that's required. And those projects pay themselves back very quickly. So if you do find that perhaps there is an adverse impact on fan power, like Jordan mentioned with the coil upgrade, there's pretty much always a way to select a fan to mitigate that and keep it lower, if not the same. So yes, it's a little bit of extra cost, but I'd wager you'd get that money back very quickly. Those EC fan retrofits, for example, often yield very good results. So, yeah.
When we saw one certain aquatic centre which prioritised a little bit of pressure drop reduction, and they lowered the flow rate of that water at the cost of heat pump COP. And certainly the back of the envelope calcs say this was not worthwhile at all. You get a lot more bang for your buck there. And a good comment here from Adam, or question there, is the idea of reducing that hot water temperature and during low demand months. Very much like what you do with refrigeration, with have a floating point, a floating pressure control. Or with a cooling tower and having the fan speed reduce when you don't have as much load. I think this is another excellent way to look at it, is in those shoulder months to have that lower, to go lower again from 60, maybe even down to 40 degrees. I don't know, Jordan, have you done much modeling on that one?
Reducing the hot water temperature during the months with lower demand.
Yeah.
Well, these heating hot water testing, you typically do it at you want to do it at during the time when it's got the highest demand. Then you can understand what your peak design parameter is. Obviously, there's nothing wrong with doing. In fact, it's also encouraged to lower your temperature during months where your demand is low too, because that's where you can benefit from heating hot, what we call heating hot water reset. It's when it's when, let's say, during months with peak demand, your required temperature may be 70, for example, but during months with lower demand, your required temperature may only be 60, right? And now your supply temperature is already lower than the peak point, and then your COP runs better. The COP of your heat pumps is also better as a result. So definitely, it does not strictly apply to this testing does not strictly apply to the months with high demand only. It also applies to the months with low demand. But like if you apply it on the months with lower demand, it's more of an energy efficiency measure, less so on identifying what the peak design point is.
That's excellent, Jordan. We might keep moving now. Thank you very much, Jordan, and please chime in for any other questions that come up later. So you've got very much a position on why to do this and starting how and some of the good steps to take. It looks like the next step is about data and getting ready for things like white certificates. So to talk about that, I'll get Andrew Clark. You're with us there, and I forget to share your presentation if Jordan may need to stop sharing there first. And Andrew comes to us from Northmore Gordon, who's been in this game for a long time, as has Andrew, helping many clients claiming the either a project-based method or a PI-M&V for white certificates. And I think we couldn't be in better hands for how to navigate getting the data in place for that one. Andrew, over to you.
Okay, so thanks, Jared, for the introduction. My name's Andrew Clark. I'm a principal consultant with Northmore Gordon. I've been doing measurement and verification for a lot of years now, both in commercial and industrial situations. And as Jared mentioned, we put together the fact sheet that is on the Race for 2030 website around the importance of metering for heat pump installations, and that's what my presentation is about today. So I'll get stuck into it. So something that has been mentioned earlier on is that metering is important from a point of view of getting the right balance between CapEx and OpEx in a heat pump installation, and that like for like is not usually the right answer. That's because the cost of a heat pump is higher than that for a gas-fired boiler, and you want to be able to make sure that you're matching your installation to the actual heat demand rather than oversizing it more than necessary. So the important question is, what is your heat demand profile? So that can only be understood well by metering either your gas consumption at a granular level, or metering your flow and temperature in your water system. And that's important to be able to understand exactly what your needs are in terms of heat. And also it helps you understand whether in the use of a heat pump, you can make use of time of use electricity tariffs. So by understanding it well, you can actually improve the business case. And the way you would do that is using thermal storage. And thermal storage can be used to improve the business case. It can minimize the size of the system that you need to install. And it can also enable you to make use of time of use tariffs and also demand reduction activities and that sort of thing. So it's very useful to be able to do that. And to do that, you need to be metering your system before you design your heat pump system. So the other question in terms of why measure is that there's potential revenues for this kind of implementation. There's a lot of interest to help drive electrification. The size of projects needs to be fairly significant for ARENA, so it's only going to be the large end of the scale that that's applicable for, but it's worth being aware of. And there's a couple of different funding programs through ARENA that may be applicable. In Victoria, there's the VEEX certificates, which under the PBA method, which is the measurement and verification method, you can potentially create certificates from a heat pump installation by replacing natural gas consumption with electricity consumption at a relatively low emission factor, which is specific to the VEEX scheme. Revenue from VEEX can be quite substantial, but it's important to understand the size of the potential VEEX creation prior to deciding on your final business case, because it can be an important factor. In New South Wales, there's also the energy savings scheme under which you can create ESCs. That should say ESC, not ECS. And that's, again, a measurement and verification method. And so for both VEEX and ESCs, you need to prove your reduction in emissions or energy change to be able to create those certificates. So obviously you're going to need to be able to measure before and after what that looks like. There's also state government grants. State government grants come along from time to time. There's a few things happening at the moment around electrification. A lot of interest from state governments. So keep your eye out for those grants, but they are also likely to need you to be measuring your consumption and your demand profile before you do the implementation, so that you can show a robust design process for your heat pump replacement of the natural gas boiler. So whichever way you look at it, measurement is going to be important for funding. And there's a number of ways to do it, and that's what I'll go through next. So in terms of what to measure, starting with a baseline, you need to understand what your system looks like beforehand to inform your project design, and then for comparison of before and after. Now, submetering at of the gas at the boiler is sometimes used for certificate creation M&V, but not always. But it's very important for being able to provide the appropriate design of your heat pump system. Now, a gas meter on the boiler is important for your design, project design, if your site has other users of natural gas that are more than a small part of the site gas consumption, because otherwise you're not going to truly understand what the gas consumption of the boiler is. The other thing that you need to be doing is understanding your electricity consumption before the implementation, because you're going to be replacing gas with electricity consumption. So if you don't have a good handle on your electricity consumption beforehand, you're not going to be able to show the difference, the change or the increase in electricity consumption for that comparison after implementation. And also you need to be have available interval data for your site natural gas consumption. If your implementation is big enough to create certificates, you'll probably be able to get hold of interval data from your gas retailer, which is pretty straightforward to do. And in terms of your system design, again, it's important to understand your heat demand. So your gas can give you a reasonable understanding of your heat demand, but generally there's a hot water tank involved at some in association with a hot water boiler. So the demand profile can actually be a little bit different to what you see in your gas consumption. And so understanding the flow of hot water and also the amount of heat that is put into the water, so temperature before and after the boiler. So that allows you to fully understand your heat demand for both project design purposes and for certificate creation. So that's your baseline. So once you have designed and implemented your project, there is you want to be able to look at the results and have a good solid measurement of the change for a number of reasons. One is to create certificates. Another is for reporting on any grant funding that you've received or aiming to receive. And the other is for provision of some form of internal reporting on the capital project to say, yes, we did achieve approximately what we anticipated we would achieve from this project in terms of energy consumption change. So similar to the baseline, you want to be measuring your temperature in and out, which essentially if you're going to be replacing a boiler with a heat pump, you're probably going to be using some of the same piping, and so those thermocouples may just be sitting in the existing pipe. You may have a bigger buffer tank, a new buffer tank, and you want to be measuring the flow from that buffer tank to the end users. The reason the flow meter there is after the buffer tank is because the buffer tank, the flow into the buffer tank won't provide a direct measure of the actual energy consumption or heat demand profile of the end users. It will smooth that out. So it's important to have that flow meter after the buffer tank. You also will want to have your, unless your boiler was your only gas consumer, in which case you could shut down your gas account. If you have other gas users, you will need to still get that interval data so you can see how much gas you're still using, especially if you're doing a certificate creation project. And of course, the increased electricity consumption of the site as a result of that heat pump installation. And as I mentioned earlier, if the hot water system, the boiler or the heat pump is the majority of your natural gas consumption currently, then you'd probably want to measure your heat pump electricity consumption separately. Sorry, if it's not the major gas consumer, then you probably want to measure the heat pump separately, because that will be the best way to inform you of the change in electricity consumption without going into detail using measurement verification techniques like regression analysis to do that. So that is what it would look like after implementation. And that will give you pretty much all the information that you're going to need to achieve what you want to achieve in terms of measuring the performance of the project. So I've covered the basics there. If you want more detail, other configurations and more detail on the process of measurement and verification, have a look at the fact sheet that's on the Race for 20 website called Measurement and Verification of Heat Pump Projects for Certificate Creation. The website link is there, and my email is also there in case you would like to get in touch for a bit more detail. Thank you for your time, and we'll go to questions, I think.
Excellent.
So
Thanks,
on to
Andrew. And
questions.
of course, the audio worked really well right at the end.
Yeah.
But it's in the fact sheet. So apologies if that wasn't going through. We certainly got the gist, missed a few bits and pieces. But that is part of the idea of the webinar today, is to say, well, you want more, go to this fact sheet here that's now published. So everything you've said today is well documented in that fact sheet, so people can get more there. Thanks very much, Andrew. Feel free to get those videos back on there, Brendan and co, as we step through now. Okay, before we move on, I think we can squeeze in a couple of questions. I'll just check if Tracy has been on the...
Yes, just a couple from the chat. Are there inexpensive gas meters that can be easily installed and removed and provide good data over the internet? From Rick Walters.
Yeah, there are some reasonably cost-effective options. The one that I like to recommend is a thermal mass flow meter. So it's essentially an anemometer type meter. They're relatively low cost, and they are intrinsically a thermal mass meter or mass flow meter. They can be inserted just through a small fitting in the pipe. As with if you don't have a suitable existing fitting in a suitable location, it will require installation of a fitting, which means shutting down the gas supply and bleeding that and purging that. So it does require a bit of a shutdown, but they are relatively quick to install, and you can either go for a network connected one or one that has a SIM card and goes direct to the cloud. You're looking at a few $1,000s for installation of something like that. If it's not a gas system, if it's an air system, you can do a hot tap, but you can't hot tap a natural gas pipe.
I'm also aware of using a simple pulse meter hooked up to the existing gas totalizer. So I'm not sure if they're readily available with 4G connectivity, but certainly a pulse meter going into the existing totalizer does work as well. And you don't need to shut down any gas lines or purge. There's the location already there on that totalizer for installing the pulse meter. It's already there, half there. Good. Tracy.
Yeah, a couple of other ones that Brendan has answered in the chat. So thank you very much for that, Brendan. Another one, is there an affordable water flow meter?
Again, I would say water flow meters are relatively low cost, and you can use the same approach. You can either put in a flange-mounted flow meter, or you can still use a insertion type thermal mass flow meter for water as well. There's a few options, and it depends on how you go about it, but there are definitely some cost-effective options there.
Great. And where can we find the fact sheet? We'll put a link in the chat here, but it's also on the project webpage, so we'll put those both here, both the generic website and the one directly to the fact sheet. And is the flow meter before and post of electrification, is it a must for M&V and claims, or can we just have gas and electricity metering as well as temperature? Typically, flow meter installations challenging and need calibration verifications very often.
Yeah, it's a good question. So the flow meter is more about your internal understanding of your system. And again, if you want to do a low cost version, you can, with a water flow, you can do a hot tap with a insertion thermal mass. So relatively cost effective.
There goes Andrew again.
Either your boundary electricity and gas meters or sub-meters. And the independent variable that is normally used will be the ambient conditions from the Bureau of Meteorology from the location, and potentially if it's a building, it may be that occupancy has an influence. So there'll be some to the certificate creation.
Okay, a little bit of trouble there with the audio again, Andrew. So we might need to close this discussion on this one down so that
Sure.
but what we will do is we'll get those questions to Andrew and we'll add them to the slideshow with answers. So when that's distributed, people will be able to see that. Good one. Andrew, thank you so much, and good job on that publication there from North Melbourne. It's going to help a lot of people. Well done. Okay, they've covered the why and a bit of the first steps and the data. One question that seemed to come up a lot, especially in the commercial market, is refrigerant choice. So with that, then A2EP set about doing a paper on this to help a bit of guidance on that selection, and hopefully make that decision a little bit easier. Brendan, if you're able to come off mute and then share your slides, you can run us through that. And Brendan's been leading a lot of this area and certainly been working in chillers and refrigeration for many, many years. So has lived refrigerants for a long time, so knows all the different requirements here. So great to hear from you on this on refrigerants. Brendan, over to you.
Cool. Thanks, Jared. Can you guys let everyone can see that? Okay. Because I've lost everyone's faces. But can everyone see this?
Yeah, we got that.
Cool.
Yep.
All right. So I think this work was very interesting, and I owe a lot of people some thanks for getting this to the point where I got it from. Particularly some of the work done early on, like ACID Consulting, was actually very, very helpful in pointing me in a direction. And then we did get a lot of assistance from a number of people. So just, yeah, impossible to thank them all. But the refrigerant guide, without necessarily wanting to be go down a rabbit hole on chemical compositions and refrigerant types and opinion pieces, the goal was, how did we get something that allowed people to make refrigerants a part of their decision-making process, or just get them a little bit more informed, I guess, than perhaps where they were before. So basically we set out and we tried to really and I think the main point that was hit on in the beginning and was the right one was, what are the standards? What are the relevant standards? And I think if I'm not going to read all of these things, they're here for text after. So if you want to know kind of what's in it, you can actually read them. But there is, for people that are not familiar with refrigerants, there's a very basic summary up front. We define what emissions come from refrigerants, and then we sort of delve through standards. What do we currently have? What would you likely have if you had a gas boiler? Do you need ventilation? Don't you need ventilation? Is that refrigerant linked to any PFAS concern? Yes or no? It's definitely not a PFAS paper, so don't grill me too hard on that. It was pretty much just finding the appropriate research to put that there. And then finally there was okay, so now we have refrigerants defined, and we have what we need to consider about where we put them defined. Now a little bit about how heat pumps work, how we can configure them, and where we would likely find that refrigerant. And then thanks to Jared for his fantastic work on the decision-making matrix because I struggled with that. We got what are the key criteria, such as cost, advantages, limitations, are the products available, yes or no. So we did get some really easy to read tables basically out of this that don't necessarily, you don't need to be a scientist or a refrigeration mechanic to figure out. I did do a test with a family member that knows nothing about refrigerant, and she was actually able to read most of it, I think 75% of it. So that was my test of whether it was anywhere near legible. So out of it, we got two really key things. One was the retrofit flowchart, which I think has been wildly popular from everybody, or this is the most feedback we get. How did we get this into 3 simple steps? Where are our boilers? Are they in a basement? Are they on a roof? Are they enclosed? Are they not enclosed? Can we, and then basically the question is, can we address flammability or toxicity? In industrial applications, a bit simpler often because they're normally handling chemicals or things already, more so than a commercial building where they're used to having the boiler in a plant room no one ever goes into, basically. So the question here was, if we can address that, we have a lot more options, and if we can't address that, we are a little bit more limited. So this flowchart has been reasonably effective, and I think a few people have used it already and given some very good feedback on it. Was a really good guiding hand on where we could start. And we also did an upgrade pathway. So getting a little bit more detailed, we said what standards are relevant for your upgrade. So if you have existing ventilation in your plant room, you need to review that. Does the plant room have adequate signage? Yes or no, whatever. All these things are relevant for an engineer that's doing your design, and they need to know what these are, and they should already know what they are. But it is also nice to have them in a very simple 4 or 5 step process that just simply says, these are the standards we need to look at. Now, as we've tested this a little bit, you do find some of the standards come up a bit shorter than what we would like. But the guide here was, and I think the takeaway was, and I think this is probably right, Jared, as a thing, is at a basic level, there was almost always a suitable natural refrigerant option. And in general, there was always a way to mitigate any risks associated with their use. And except in some very rare cases where plant rooms are not able to be ventilated or they have significant constraints. So for example, there's no space. You're right next door to something, then you must have louvers and you must enclose a plant room. You might limit what you can do with propane in that instance, for example. We've seen a really good case study through A2EP of a winery with a really good example of signage, which was done by, forget the heat pump manufacturer, it was Blue Box, I think, at one of the wineries there. And that was a really good example of putting this into practice on signage and raising awareness for those on site. So I guess in summary, the goal here was really simple. It wasn't to write a chemical chemical composition paper on refrigerants or talk about PFAS. It was what standards are relevant, what refrigerants can we use, and when you get thrown options, maybe a building manager or somebody gets an option from a supplier, they'll at least be able to look at something and say, am I being proposed something that makes sense? And is there a pathway for me to use a natural refrigerant? Because I think that's the way. I think that's the way forward, is using natural refrigerants wherever possible. So this is where we went here. It's probably something that needs a lot more work, I think, or could have a lot more work done. And in that vein, there is a little poll that we'll send out after I get done talking about heat pump estimator, which is, what would you like to see in a refrigerant guide? And then you can also ask some questions at the end, of did we cover this, did we cover that? And basically I'll try and answer those as best I can. Moving on, we get to my favorite part of this whole project, which was my big nerdy spreadsheet that we converted heat pump estimator V1 into heat pump estimator V2. We got to do some really cool things in here, like add part load performance curves. We got to add some new refrigerants. We also got to add a seasonal COP and pretty much get very granular, looking hour by hour in a given location at the actual weather profile, at a percentage of a given heating load at any given point. And pretty much we have what is known, I guess, as an hourly simulation method, which is very common in most energy modeling tools. And because we got hourly, we could do things like grid emissions, we could do things like wholesale prices, and that opens the door for a lot of potential future features. Rather than do this live and break the tool, I did record an example. I kind of cheated. I did record an example last night. quite late because that's when I spent most of my time on this tool. So here we go with a bit of an example. So what this is going to show you before we start is me looking pretty much at the example that we did a case study on, which is a meat processing plant where they actually need 85-degree water. But if you do 75-degree water, I'm going to show you how the tool can be used to model the difference in payback by using those two things. So we're going to go through this step by step. So we start off, we have a brand new landing page. It does give you a bit of information, but some of it is the same as before. But we do have some new information there on refrigerant classification. You have a couple of ways to log in. You can create a password, or you can use LinkedIn or your Google credentials, and you'll just get in to the tool. There's no sort of secret passwords. It'll bring up a screen that says Start Wizard and then ask you to define your existing site. So in this case, I'm going to choose Melbourne. I've got some pre-built load profiles here. You can choose them from the right in this little profile library like I'm showing you now. Or you can choose them from the drop-down box up the top, whatever floats your boat. Depends if you're visual or word-based. We can then also move these load profiles left and right, move our peak left and right. We can change the shape. We can let you manipulate a little bit of that. When you do that, it will actually change the outcome. Next step is define when we're actually open. So I will freeze here just for a second. The facility itself could be open from 9 till 6 every day. It could be open 9 to 6 Monday to Friday. It could be open different hours on different days. So we catered for all of that. You can actually adjust all the days at once. You can adjust just weekdays. You can adjust the Monday. Yeah, you can do whatever you like here. Whatever you set is what the model will run off. There is no restriction. You can run 24 hours if you like. You can do funky stuff like set it to start at 2 a.m. and finish at 10 p.m. You could do all sorts of whatever it is, whatever kind of shifts there are. I knew that was going to happen. It was going to break when I did it. So it wasn't even live and I already broke it. So here I am changing from 9 to 7, and then I'm going to turn off Sunday. So that was how easy it was for me to change that profile around. It's now going to bring up some of the questions you were familiar with before. What was your average heat or your average water flow? What was our heat required and what was our peak? How often do we see the peak? And what water temperatures do we want? So this page is pretty much replicating what we had in the previous tool. If you've used that, you'll be relatively familiar with it. You'll notice the tips along the way that are little guides for how to enter that information. If you do something wrong, it will correct you. There is some error correction. Probably need to enhance that, but it is there. And now we go, what are we costing for our gas? Let's call it $18 a gigajoule and 25 cents a kilowatt. On this option here, if you do know your annualized heating cost, then I'll pause. You can enter that and it will use that, providing you're not wildly away from what our load profile calculates and what our system efficiency number is in the background. Because sometimes you'll get a gas bill, it won't be broken down as granularly as what it probably needs to be. We did talk about metering before. If you had very accurate metering, you could type the number in and we would run off that number. It would let that number through. So here we can choose our heat pump and we have an array of options. We have water, ground source, or air source. Kind of speaks for itself, but air source will run off the ambient temperatures for the location. Water source will run off a temperature that you provide, which I'm showing right here. And ground source will run off the pre-built input temperatures in the background of what the groundwater temperatures are specific to your location. So I'm going to choose 40 source water. I'm going to choose an ammonia heat pump. And then we're going to hit next. Now it's going to ask me what, why did it do that? It broke, sorry about that. Now it's going to ask me here, what do I want in terms of heating for my thermal storage? And this is kind of brand new. The idea here is when you enter in your average up front and you enter in your peak, it will do a division and it will say, okay, you're running at 60% average. Now, if you wound that down to 50, all that's going to happen is the optimization solver in the back is going to let the system rely a little bit more on water and thermal storage. So you'll possibly increase the size of thermal storage and decrease the heat pump. If you do wind it up and you say, no, I'm actually happy with 70, it'll do the reverse. So it'll make the heat pump bigger and the thermal storage smaller, if that's the case. So that's the number you're entering in here. And then finally, do you want to consider load flex or demand response? If you want maybe a 3-hour outage, you would type that in here, basically, and it would add that water storage. Now we pause on our output And we can see we've got our energy usage, we've got our heat pump size, we've got our seasonal COPs, and sort of some other really cool things here. We have estimated dimensions for what the heat pump will actually take up. We have a thermal storage calculated number, and we have an area for that as well, and we have a simple payback. Doesn't start wonderful, starts at 15.9 years, but that's kind of normal, which is where the certificates come in. And we say, okay, do you want to claim certificates like we talked before? So you've got VIX, ACCUs, ESCIs all built in. They're a 3-month average rolling price. We kind of can update those as we go. I know there's thing, and you see my payback is now increasingly better using that funding, no matter which certificate I use. And that source of revenue is going to help that project payback. Noting we're only looking at the storage in the heat pump itself here. Now I'm just going to quickly, just as an example, wind it down to 75. And we're going to go back through the steps, which will all be the same. I'm not going to change anything else. And now if you have a look, my full load COP and my seasonal COP have improved. My heat pump size didn't change, but my payback is now 10 years. So Jared's logic before of, it gets better as you decrease that temperature does show that. The curves in the back will actually reset that for you. If you want to send the outputs, you hit the button here in it and it sends it to you as a report. So you can run all sorts of scenario analysis here. We could go back and we could change the refrigerant type. We could change the to an air source for the same scenario. We could do whatever you wanted, pretty much. You can run as many as you like and just keep emailing to yourself. If you want to restart, you can start a new project and say, keep the existing or move on, and you'll go back to the start. That kind of summarizes how you navigate through the tool. It's potentially got a lot of things to improve. I threw some ideas here for inspiration. I'm not going to read them. I'm not going to read them all, but I get super excited when I think about how we could actually bring in wholesale power into the actual energy calculations, and we could bring in all the demand response programs. We could model cascade systems. We could do some more advanced financial modeling. We could implement waste heat recovery. We could put a heating profile generator in there from your data. Yeah, heaps of stuff we could do. The solver that solves for the size and everything is built here to scale. So if there's any options that you can think of, feel free to add them to the chat or reach out and we'll see if we can add them. That kind of summarizes how the tool works. And that's
Excellent.
it. If there's any questions.
Brendan, thank you so much. Let's just have a quick check if there's one or two questions. Tracy, have you seen anything coming through?
Yep.
Questions there?
There's a couple in the chat from Peter. Does the heat pump tool apply to potable hot water loading commercial buildings? And does the calculator derate this carbon dioxide heat pump COP with a closed loop heating application due to higher return water temperature?
We start with the easy question. I'll call them easy, but they're the toughest ones. So does the heat pump tool apply to potable hot water? The load profiles aren't built like that now, but it easily could. We could easily build a load profile in that does that. They're built at the moment for space heating. Now, the other question of does it derate the CO2 heat pump? It has a curve on efficiency that does change based on lift. And it does change based on difference between the source water temperature or the source air temperature and the actual output. So it will actually derate performance. And the higher lift you go, there is actually some advanced economics functions in the back, which will actually increase then the dollars per kilowatt as well as we increase that lift and we bump up as well. So short answer to both is one we could build and the other one it's already there.
Great. There's another one. Does the calculator take into account any warm-up pip-up factor in boiler capacity sizing? If so, typically what percentage is being used to account for this?
Yeah, so nominally speaking, depending on the type of profile at the moment, we allow a pretty simple run on like hour. Like if you set 6 a.m., we'll assume you're starting an hour before that. Could be right or wrong. I'd love to adjust that. It's not hard for me to adjust that. So if anyone has any ideas that can enhance that, feel free to reach out. But it doesn't assume that you start your facility at 6 and the heating starts at 6. It'll generally come on an hour before that. That just sort of followed some of the neighbors' rules there. I didn't make that up. It just kind of came out of the guideline for neighbors on a warm up in the morning. So if there's anything else I should be doing, then feel free, share the feedback and we can figure that out. But it's not necessarily a percentage.
And one last one, can the tool also estimate cooling loads?
Yeah, and I'd love it too, but no, not at the moment. I would love to integrate cooling. The previous one had a cooling COP in there, but it didn't really change a lot, so I didn't put it back in. But I could easily integrate something about cooling, but we're really worried about heating. Yeah, so we didn't add cooling. We could have a cooling load profile and then run a curve for cooling off a simultaneous unit or something different if needed. But yeah, it wasn't in the brief up front. So at the moment, no.
Okay, Brendan, thank you so much, and Tracy, thanks for managing that Q&A there. Fabulous. And Brendan, we'll send that around with that. The video will go out with this recording, so people will be able to refer to that and help them guide them their way in the usage of that. So good job. Thank you.
We'll also record how to use guide to go with the tool, which will be another video with me. Maybe someone else's voice, possibly not mine, but it'll be, it might be a computer enhanced version that doesn't sound so Australian or something.
Very good. And so to finish off now, I did have up the front, we had case studies, and sometimes that's where you'll start looking at case studies and see what's out there. But sometimes it's what you'll use at the end after you've done some investigations and say, right, this gives you some more confidence of what's to do there. And so to take us through a few of the work that we've done with case studies and with updating websites so we can get the information to you, we've got A2EP's communications hero, Laura Taylor, is going to take us through that one. She doesn't like take compliments well, but this is still worth it.
Thank you, Jared.
Laura, take us through how we've got all these case studies and everything together.
For sure. Am I on the right showing screen?
I've got resources from this project, yes.
Fantastic. Okay. Yes, before everyone takes off to take the heat pump estimator for a spin, we just wanted to go through the resources that have been developed through this fantastic Race for 2030 project and that we've been talking about today, and where you can find them. So Jordan's presentation was talking about the roadmap and assessing feasibility for the heat pumps. So that is the first guide that we have there. You'll find it actually called Retrofitting Commercial Buildings with Heat Pumps, a how-to guide. And then we have Andrew's fact sheet, the measurement and verification fact sheet, the refrigerant guide that Brendan just took us through, the heat pump estimator, and I'll talk about the case studies in a moment as well. Just to confirm, we're making it really easy for you to find these. We've got them in 3 locations for you. So we've got it on our futureheat.info website, which is a dedicated website about decarbonising industrial and commercial heat. We've got all of those tools and case studies on there. They're also available on the RACE website there at that link there. And we also have these available on the A2EP website. So you can't say you can't find them. They're in 3 different places. But just to be sure, after this webinar, in addition to sending out the recording coming from RACE, we will also be sending out direct links to each of these resources for you to find them. And just before you head out for lunch, let's just have a quick look at the case studies that were developed for this project, because they really are rather fantastic. And we've got a number of them from New Zealand as well, because New Zealand really seems to be setting the standard and going ahead of Australia in terms of implementing heat pumps. So we had some really good ones from over there that were shared with us through data consulting. And the first 3 of those are actually food and beverage ones. We've got Ansco Foods based in Canterbury, and then also Alliance Group, which was a meat processing site in Nelson, New Zealand. And then the 3rd one, another meat processing site, is the Hardwicks Meats Processing Site, which was actually an award winner from the Australian Renewable Heat Conference. And that was a project through Hoctor Refrigeration, also implementing Mayakawa Australia heat pumps. So we've got those 3 case studies there, which are really fantastic. And we also have some commercial ones that we think will be of interest. So St John of God Hauora Trust Care Home, which is another one through DETA, and that is a multi-residential site with a heat pump used for the domestic hot water there. Timaru Hospital in South Canterbury, where they used heat pumps to replace a coal boiler. And then we also have the Cabarita Swimming Centre, which was a fantastic project carried out by Ream Australia, a really beautiful picturesque swimming pool there, but they've had fantastic gas savings at that site. So it is worth checking that out as more and more councils are converting to heat pumps. And just on that point, we have a lot of resources on the A2EP website as well to support those councils. Got the second round of the Community Energy Upgrades Fund open for applications now. It's really worth checking out this case study and the other resources that we have available for you there. So, Jared, with that, I will leave it there and let everybody have their lunch.
Fabulous. Thank you so much, Laura. So yeah, plenty of great resources there to take you from start methodology and sizing and modeling, the whole suite of things there. And often, you know, these tools and what have you, just to get you started, just to get you moving. You are going to need to work with a lot of different consultants and suppliers and what have you. But this will hopefully then get you started there. Excellent. Okay, Tracy, any questions on this before we start to wrap up?
No final questions. Just from Race's perspective, we'd really love to thank the entire project team that worked on this. Fabulous job, and hopefully this will really help with the bottom-up integration of heat pumps into sites, commercial and industrial. And as Jared mentioned, through the working groups which we have coming up, we're hoping to look at how we can do further work to continue to support heat pumps and cost-effective heat pump integration into commercial and industrial applications in Australia. So thanks very much to the team. Great work.
Thank you so much, Tracy. Excellent. Okay, let me just give you a quick update of little bits and pieces going on around the place. So over the next week, we have a lowering the heating hot water temperatures in commercial buildings, a workshop in Melbourne. That's there's still positions available for that for next Tuesday. And so that will just be a workshop discussing how to do this, and very much what Jordan presented before. But looking at the different challenges and the risks involved with the change and methodology and communication. So we're looking forward to a great discussion there. The day after that, we have a member meeting, A2EP member meeting on the 16th in Melbourne CBD. And then later this month, we're also doing that heating hot water workshop in Sydney. Both of those workshops, we're going to do some site tours as well, checking out heat pumps or at least boiler systems that are about to go through these upgrades. So a great combination of discussion and hands-on there as well. Okay, and just another reminder there, we do have our Australian Renewable Heat Conference is back for 2025. So get that one into your diary, 26th and 27th of August in Sydney, in a fabulous Illumina brand new conference venue right in the middle of town at Martin Place. Looking forward to that one. It's going to be focused on real projects. Once again, we'll be hearing from those that have implemented the projects, the lessons learned from those, and how everyone else can do the next generation of renewable heating. Focus will be on electrification and bioenergy. That's where the main game is for decarbonising process heating at the moment. So that's where we'll keep our focus there. If you want more A2EP, go to LinkedIn and follow us there. Lots of updates and links and to keep you well informed what's happening in energy productivity and decarbonisation. Otherwise, that's it for us for this webinar. Many thanks to our presenters today. Thanks to Jordan, Andrew, Brendan, and Laura. Tracy, great to have you with us there as well, helping with the Q&A. So thanks for joining us today. And I hope you enjoy the rest of your afternoon. We'll have the recording and the slides with the Q&A out to you in the next few days. Thank you so much.